This video is going to cover how to construct energy bar charts for physics. So first we're going to start off with the definition of energy. Energy is a conserved, substance-like quantity with the capability to produce change in physical systems. The total amount of energy within a system does not change unless energy enters or exits the system from the surroundings. This is an equation that can represent that. All of our initial energy would be equal to our final energy unless we have some change in energy of our system. Energy enters or exits a system by radiating, represented with a capital R, heating, represented with a capital Q, or working, represented with a capital W. In a physics class, the mechanism by which energy enters or exits a system will most often be the mechanism of working. Any energy that is gained by the system has to come from the surroundings. We can represent that with this equation. Any change in energy of our system plus any change in energy of our surroundings is equal to 0 joules. So if we have a positive change in energy of our system, that would correspond with a negative change in energy of the surroundings. And when we add those two values up, we would end up with a value of 0. And conversely, if we lose any energy from our system and have a negative change in energy of the system, that would correspond with a gain or an increase in the change in energy of the surroundings, but they would still sum up to equal 0. Now, when energy is within a system, it is stored within that system in different energy accounts. It can be stored as kinetic energy, represented with a capital E for energy and a subscript K for kinetic. That's the energy that would be associated with motion, the motion of an object. We have our gravitational energy, capital E for energy, subscript G for the gravitational energy. This is also known as gravitational potential energy, and it's the energy that is associated with the height of our object. We have our elastic energy, capital E for energy, subscript EL for elastic. That is the energy that's going to be associated with our system that can be stretched or compressed and would naturally return to its unstretched or uncompressed state. And then finally, we have our thermal energy, represented with capital E for energy, subscript TH for thermal. This is often called E dissipated or E internal. Essentially, this last energy storage type is going to kind of be a leftover account of if we don't have any energy associated with our motion, our height, or, well, compression or stretch, but we know energy is internal to our system, we'll typically associate with this account. Now, if we're focusing on all of our initial energy that is stored within a system, we're going to be focusing on all of what the energy within a system is doing. So our total initial energy would be the sum of the initial kinetic energy, the initial gravitational potential energy, the initial elastic energy, and that initial thermal energy. And then likewise, if we're figuring out the final energy within a system, we're focusing on all of the final kinetic energy, the final gravitational potential energy, the final elastic energy, and the final thermal energy. Overall, this equation, our initial energy plus any change in energy of our system is equal to the final energy, is a simplified format of showing all of these potential energy storage types right here, plus any of those mechanisms via working, would be equal to all of these final energy storage types. This is a lot to represent. This is why we want to have graphical representations of energy storage. One of the ways that we can do this is with our energy bar charts. Energy bar charts can be used qualitatively and eventually quantitatively to account for the transfer of energy into or out of a system, how energy is stored within a system, and those energy bar charts can also be used to construct an equation to represent that conservation of energy. This is what a very generic energy bar chart would look like. We have a bar chart over here on the left that would represent the initial energy stored within the system. We would have our bar chart on the right that would represent the final energy stored within the system. We would have this circle in between the two bar charts that would represent our system itself, that we can show any energy flowing into or out of to account for any differences in the energy stored within the system between the initial and final accounts. Now, there are several steps that I'd recommend we follow when we're trying to construct our energy bar charts. The first step is really the first step that I try to focus on in pretty much any problem within physics. It's to identify and communicate what our system is. So, step one, identify the system being observed by writing that system in the circle. Now, when you're looking at an actual problem to do this, you'll figure out what the system is by actually analyzing the system. But the way you can communicate what the system you're analyzing is by writing your system within that central circle. Once you have identified what the system is, then you're going to construct that left bar chart. So fill in the left bar chart by identifying what the energy within the system is allowing that system to do. And then the more of that energy we think is stored within that specific type, represent with more bars of energy. Because really, while we do have discrete bars here for the different energy storage types, the y-axis here would correspond with the total amount of energy we're thinking corresponds with that energy storage type. So go through and construct it. For EK, is our system moving? If it's moving slow, it has a little bit of energy. If it's moving fast, a lot more within this account. EG, is the system at a height above a reference height of 0? If it is, it has a little bit, and the higher up it goes, the more EG we're going to represent stored within the system. Elastic energy, is any part of our system compressed or stretched and wants to return to its natural state? The more compression there is, the more energy we have stored there. And then finally, any other energy we know needs to be within the system, we would just throw into the ethermal account. Typically, I don't include any energy stored in ETH at my initial state. Once we have accounted for all of these different energy storage types, we're going to do the exact same thing with the right bar chart. So is the system moving? Is that a height above 0? Is any part of it stretched or compressed? And then do we need to account for any other energy stored within our system? Once both bar charts are constructed, we should be able to see whether or not the two bar charts would have the same amount of energy stored within the system. If there is not, and we have no way to explain why they are not equivalent, this is where step 4 comes in. When there are different amounts of energy stored within the system between the initial and the final state, we need to show how that energy flowed into or out of the system, that change in energy. And it's also useful to represent and try to figure out what the mechanism by which that transfer of energy occurred. In physics, if energy transfers in via the mechanism of working, that means you need to have a force external to our system causing a displacement of our system. If you do not have an external force to the system acting on the system, that is causing a displacement. There is no transfer of energy within our system. Once all of our energy has been accounted for, the initial energy, the final energy, and any changes in energy, then we can go to step 5, which is to write an energy conservation equation. This is based on how energy is stored within the system and clearly shows if energy flows into or out of the system. So our initial energy plus any changes in energy to our system is equal to our final energy. And likewise, if we end up with less energy stored in our system in the final case, this plus sign can just be replaced with a negative sign. But these are the 5 steps we need to include every single time we're constructing an energy bar chart. These are the 5 steps written, well, in a slightly condensed way, all together, as well as what a small version of our energy bar chart would look like, as well as a qualitative energy conservation equation. We can make this quantitative by actually writing all of the initial changes in energy and final energies in terms of the equations for each of these energy storage types and actually solving for the value of any part of this system. Now, I really want to emphasize this 5th and final step of writing our energy bar charts. That is to write an energy conservation equation. The reason why I really want to emphasize that is ultimately this is why we want to construct energy bar charts. Not just to have a visual representation of how energy is stored within our system, but to use it as a visual aid in constructing that conservation equation for us to end up trying to use it to solve for complex problems involving energy storage and transfer. Now we're going to go through an example using that same example we had back when we were talking about energy pie charts. We had a ball that was going to be at location A pressed down onto a spring that was fully compressed. The ball was not moving and it was at the lowest possible height. At B, the spring became uncompressed. It pushed the ball upwards, and this is the instant the ball has left the launcher. It is moving upwards really quickly, and it is at a greater height than it once was. C, the ball is partway up to its maximum height. It's still moving, but it's moving slower than it was at B. And then D is when the ball is is at its maximum height, and it is temporarily not moving. Its instantaneous velocity at its maximum height would be 0. Previously, we represented our energy in the form of pie charts. The size of each pie chart represented the total amount of energy we had within our system. And then we talked about what percent of our system could be accounted for in each energy storage type. We said that all of the energy was stored in the spring at location A, so it was elastic energy. At B, most of that energy was being used to move the ball, and then a little bit of it was associated with the height of increase of the ball. At location C, we have a split between the kinetic and gravitational potential energies because the ball was moving slower than it was at B, and it was at a greater height than it was at B. And then finally at D, all of the energy within the system was associated with its maximum height. We're going to take the same scenario and then try to construct some energy bar charts. So right here, I put an energy bar chart directly underneath each pie chart. So we already know how energy will be stored within the system, but we do need to represent it qualitatively in the form of energy bar charts. The first step we need to do is to identify the system. You might notice that I do not actually have the system identified as circles in between each bar chart. I'm just putting it off to the side right now just to try to cleanly represent how energy is stored at each bar chart. But my system is going to be the ball, the spring, and the earth. I'm representing this with that dash line on each of those diagrams for A, B, C, and D to show that our system is including everything. And when I do include Earth in my system, what I'm really referring to is the gravitational field of the Earth. What that means is that force of gravity, that is the interaction between the Earth's gravitational field and a part of our system. That force would be internal to our system, so we wouldn't have any external force acting on our system from that force gravity. This allows us to actually include our gravitational potential energy as an internal energy storage account rather than a transfer of energy between the system and the surroundings. But now that we have that system identified, we can set up our energy bar chart, in this case the leftmost bar chart, location A. So the ball is not moving, so that's no kinetic energy. The ball is at its lowest possible height, that's reference height of 0, we'll say, so we have 0 gravitational potential energy. Our spring is internal to our system, and it is compressed. The spring wants to return to its uncompressed state, so we're going to be storing a lot of energy as our elastic energy. And then I'd never start off with thermal energy unless I have no other reason to do so. Next step would be the right bar charts, but you might notice we have 3 other bar charts to include. So I'm just going to work my way left to right, and we're going to focus on all of our energy bar charts first before we move on to transfers of energy and the conservation equation. At B, the ball is moving. It is moving really fast, so I put most of the energy within our system as kinetic energy. The height has increased a little bit, so I'm putting a little bit of energy as gravitational potential energy. There is no compression in the spring, so I have no energy stored as my elastic. And then I have, well, all of my energy accounted for. I don't really have any source of any thermal energy, which is going to often be associated with the force of friction. So this is how my energy is going to be stored, mostly kinetic and a little bit of gravitational potential energy. At location C, the ball is slowing down. It is accelerating downwards while it's moving up, so it will be slowing down, so I'm showing even less kinetic energy. It's at a greater height, so I'm showing more gravitational potential energy. Nothing has changed about the spring, so I'm leaving it as 0 elastic energy, and there's no source of friction or any other energy, air quotes, lost that I need to account for, so I have no thermal energy at location C. And then finally at location D. At its maximum height, the ball will temporarily have a velocity of 0, so there'd be no kinetic energy. It's at its maximum height, so I have a lot of gravitational potential energy. There's still no compression in the spring, so no elastic energy, and once again, I do not need to include thermal energy in this account. All of my energy in each of these bar charts is conserved. I have 4 bars of energy total represented in each of these 4 bar charts. I can explain what the energy is doing in each of these situations based on these energy storage types, and I have no forces external to my system that are causing a displacement of my system, so I don't have any work done on my system. So at this point, I can write my energy conservation equations. The only way I have energy stored at location A is as elastic energy. So I have E for energy, subscript EL as elastic, and I'm also putting comma A to say it's the elastic energy at location A. That is equal to how energy is stored at location B. We have our kinetic energy at B plus our gravitational potential energy at B. That is equal to our kinetic energy at C plus our gravitational potential energy at C. And all of that is going to be equal to our gravitational potential energy at D. Now, this is actually why I'm including A, B, C, and D as part of my subscripts, is because for locations B, C, and D, they all share the same type of energy storage, gravitational potential energy. And I want to be able to differentiate between the energy associated with the height at each of those 3 locations, because it would not be the same amount, so I want to label it slightly differently. But this right here is going to be an example of how we can construct energy bar charts when we have a constant energy internal to our system that is not experiencing any changes in energy. We can look at the same situation, but change our system. What I mean by that is if I were to identify my system as the ball and the Earth's gravitational field, but I neglect to include the spring, we might have similarities between our energy bar charts, but the identification of the system, that first step, will dictate what the correct answer is for our energy bar charts. So, when I have identified my system at location A, our pie chart is saying we should have elastic energy. However, our pie charts did not actually focus on a system analysis. Focusing on our system, we have our ball and our Earth. The spring is external to our system, so we're going to discount that from how energy is stored within the system. At location A, no part of our system is moving, so there's 0 kinetic energy. At location A, the ball is at its lowest height, so we have 0 gravitational potential energy. At location A, we have no part of our system being compressed or stretched, so we're not going to have any elastic energy at location A. And then we have no other energy that we need to associate with that thermal account at the beginning. So we don't have any energy represented within our system at location A based off of this system. Location B, the ball is still in motion, and it's at a height slightly above where it once was. So we're actually going to represent it as exactly the same amount of kinetic energy and gravitational potential energy as the previous system analysis. We can do the same thing with location C and D. Nothing about the motion of our system or the height of our system has changed. So we still have the same energy storage for locations B, C, and D. And we can have the last three parts of our conservation equation remain exactly the same. But this is where we need to show, with that conservation equation, how these equal signs can be true. Because right now, we have 0 energy stored within our system. That is 0 joules of energy. That means we must have some transfer of energy. This transfer of energy is going to be via the mechanism of working. We have a force acting on our system, crossing the system boundary. That is that force, that is that interaction between the spring and the ball. That is a force that originates outside of our system, acting on our system, that is displacing our system. That would be the work done. Looking at our bar charts, though, in this format, we're not actually seeing any energy entering our system. We're seeing we have energy in our system at B, C, and D. Our conservation equation is saying we have a transfer of energy, but we need to actually include energy being added to our system. When that occurs, we definitely want to include that system analysis in between our bar charts. This is the way that can be set up. We have our energy bar charts in the same way they were previously. But we've also included that system/flow in between each bar chart. Between points A and B, we have that energy transferred into our system. So I have how much energy is transferred into our system. Well, crossing that circle that represents our system. I have an arrow pointing in the direction that energy is entering. Our energy entered our system between A and B. Between B and C, that energy remained within our system. Same with between C and D, the energy remained within the system. That's why we're not showing any energy entering or exiting our system in that case. But these are going to be our energy bar charts, where a big part of this is we are now able to represent how energy enters or exits the system. We have ways to start relating our analysis of energy storage to a mathematical representation of energy storage using those conservation equations. And this is going to be the format that I recommend moving forward for how we're going to represent energy stored within a system and energy transferred into or out of a system.